Richard James Mathematics Resources will present Grade 4 Practice Paper 4. For each practice paper, we have 4 video presentations. Each video presentation from A to C will have the solution of 12 problems. The other video, which is video D, will have the solution of problems going all the way to the end, which is problem number 49. So on this occasion, we will just begin our presentation of the 12 problems that we have for video 4A. What is the sum of 1,479 and 186? If we are required to add numbers, we will do well to make use of the place values of the numbers, or the place values of the digits that are in the number. If we can somehow have the numbers properly aligned, then there will be no need for writing down the place values. But at this stage, it's a very good thing to always include the place values. We will begin by writing down the first number. Take note of the place value of each digit. Jerry, please give me those place values. The place value of the 9 is
1,
7,
10,
4,
100,
and 1.
1,000.
Okay. Next, write 186 by first placing the ones digit under the ones digit. So we will have those digits properly vertically aligned. The ones digit will be placed vertically aligned with the ones digit of the other number, and we'll do the same for every digit in the number. So the next digit that we will have is the 10th digit of 86, which is the 8, and it will be vertically aligned with the 10th digit of 1,479, which is 7. And finally, place the hundreds digit under the hundreds digit. So the hundreds digit will also be vertically aligned with the hundreds digit of the other number. That is very important, because when we are adding numbers, digits of the same place values need to be added together. Write your addition sign and draw your line. When you are adding, make sure that you have all of your forms in place. When we are adding, we need to ensure that we include the addition sign, that somebody who is reading the solution of the problem that we have will be able to determine that we are actually adding. And it is important for us to separate the problem from the answer by making use of that horizontal line. We will go to the next slide where we will complete the addition process. Before we have any information on the screen, I will ask Jerry, which digit do we add first?
The 6 and the 9.
And what's the place value of those digits?
1s.
Okay, so we will add the ones digits first, and we will therefore add the 6 and the 9 by adding the ones digit. Nine plus 6 is equal to
15.
And I'm asking before I put the information on the screen to see if Jerry is sharp on his addition. And what do we do with the 15? Do we put 1 5 below here?
Yes, put the 5 down and carry the 1.
Okay, so we will put the 5 down and carry the 1. Place the 5 in the ones column and carry 1 to the tens column. What do we add next?
8 and the 7 plus the 1.
Okay, so we need to also include the 1 that was carried from the 1's position. Notice that what we have there is, right there, is 15. And we know that when we are adding, that the 1's digit is retained in the present place value, and the 10's digit is carried to the place value of greater significance. So let us add those. So we have 1 plus 7 plus 8, and that is equal to 16. And we do the same. We will place the 6 in its rightful place in the 10th position. Then the 1, which is in 16, this 1 is the 10th digit in 16. It will be carried to the more significant position or place value position. So place 6 in the 10th column and carry 1 to the hundreds column. And students like to add these or add like this when they do not have anything to carry at all. Add the hundreds digits. What do we get?
6.
Right, so 1 plus 4 plus 1, and that is equal to 6, and we do not have anything to carry. So place 6 in the hundreds column. Well, if we are adding the hundreds digits, then the result must be placed in the hundreds column. And finally, there's nothing to add to that one. So we have only that one in the thousands column. It will return as it is. So there is our answer. Can you read that number, Jerry?
1,665.
Great. So the correct answer is option D. We are required to find the result of 15 divided by 3. So what is 15 divided by 3? This is a division problem. And in grade 4 and throughout your primary school time, students need to know how to express or the form in which numbers are written when we are required to divide. So we will begin with 15, which is the dividend, and we have that symbol that we use for division, not only a symbol but also a form in which we have first the divisor and on this line here the result of division, which is called the quotient, will be placed. We will first attempt to divide 3 into 1. We can't, so we say 3 into 15, and that equals
5.
Right, and place the 5 above the 5. The correct answer is option A. We may take an approach that makes use of the fact that division is the opposite of multiplication. So we may solve this problem in another way. Division is the opposite of multiplication. And if we understand our multiplication table, if we know them, then division is very simple to us. So there we have the dividend, we have the divisor, and the answer is called the quotient. If we multiply the divisor by the quotient, the result will be the dividend. what number do we multiply by 3 and the result is 15? So when we are required to divide, like say 3 into 15, we may also say, what number do we multiply by 3 and the result is 15? If we can answer that question, then we are able to divide. And that question may be easily answered if we know our multiplication table and we are sharp on our multiplication tables. We should have the answer at the tip of our fingers if we are sharp on our multiplication table. If we are sharp on our multiplication table, then we can answer the question, what number do we multiply by 3 and the result is 15?
5.
Right, so Jerry is very quick to say 5. And what I am doing with these animations is make sure that I do not give you a very long time to take a look at what is going on, because you should be sharp on your multiplication table. Because you should be sharp on your multiplication table, then we are just going to give you a glance on it. There it is. And the answer is 5. 5 is the number that we multiply by 3, and the result is 15. Therefore, if we divide 15 by 3, the result is
5.
There. We need to perform the operation as given, and it requires that we multiply the numbers. So, Jerry, how do we know that we are required to multiply?
The sign.
What is the sign for multiplication? It looks like an
X.
Right, it looks like an X. And we know that we are required to multiply. And we will multiply. When we are multiplying, which digit do we first multiply by 7?
The 6.
Right. And what is the place value of the 6?
1.
Right. So if we are required to multiply, we will begin with the digit of least significance, the one with the smallest place value. And right there is where we begin our multiplication. So we have our place values in place right there. As a reminder, constant reminder, that means by the time you are through with these grade 4 numeracy exercises, you would have been very sharp on your place values. When multiplying numbers, we begin with the numbers at the right. They are the ones with the smallest place values. And we always say also that it is the least significant digit. So we multiply 7 6s.
42.
All right, Jerry. You are very sharp. 7 3s.
21.
All right. 7 4s.
28.
All right, because I was saying I'm not using a number that is not on the screen to see if Jerry was prepared. And of course, he is very sharp on his multiplication table. So we have 7 6s 42. Write down 2 and carry 4 to the next column. The place value to the immediate left is always 10 times the present place value. That is why for each result, the tens digit is carried to the left. So if we add or multiply, we end up with a result. This number is 42. So this number on its own has 2 ones and 4 tens. The tens digit will be carried to the digit of greater significance, which is located to the left. And we will retain this digit in 42, which is the ones digit, in the column in which we are working. So we are working in the ones column. 2 is placed in the ones column. The 4 is a digit of greater significance. It is carried to the column of greater significance, which is located to the left. Multiply again. So on this occasion we say 7 threes,
21.
and to the 21 we will add
4.
When we add 4 to 21, the result is
25.
right, and we have 25. The 5 will take its rightful place in its present column or place value column, and the 2, which is a digit of greater significance, will be carried to the column of greater significance. So write down 5 and carry 2 to the next column. Finally, we say 7 1,
7.
and to that 7 we will add the 2 that was carried from the column of less significance. So we will add to that 7, we will add the 2, and the result is 9. So write down 9. After writing down 9, there is nothing to be carried. The correct answer is therefore option D. Here we have another division problem. The statement of the problem says explicitly divide. So we have right here in the statement of the problem telling us to divide. So we will divide 1860 by 3. So we will arrange again our numbers with the division format. We will first attempt to divide 3 into 1. And we can't. So we say 3 into
18.
And 3 into 18 is?
6 times.
Right. And when we are dividing, if we are dividing by 3, then we will pay attention to our 3 times table. So if we are required to divide by 3, we focus on our multiplication table, our 3 times table. And if we are going to say 3 into 18, we say what number do we multiply by 3, and the result is 18. The result is 6. Therefore, 6 will go there and placed above the 8. Would it be wrong, Jerry, to say 3 into 1? I can't. So put a 0. Would that be wrong?
No.
It would not be wrong. But because the leading 0 does not affect the value of a whole number, we do not have to include that 0. Next, what do we say?
3 into 6.
3 into 6 will give you?
2 times.
Right, because 3 2's 6. So if we are dividing by 3, and we need to know 3 into 6, then we say our multiplication table, and if we say 3 2 6, that means 3 into 6 will go 2 times. Right. Divide 0 by any number and the result is 0. Now, here's a question for you, Jerry. We need to say 3 into 0 and the result is 0. Does it matter if we put the 0 here or not?
Yes, it matters.
Okay. Right. So it matters. Put the 0 right there. The correct answer is option.
C.
If we did not put the 0 here, then the result would be 62, and that would be incorrect. It would be incorrect for quite a few reasons, one of which is if you multiply 62 by 3 you will not get 1,860. So if we divide and we get a particular result, we can check our answer by multiplying the answer that we get by the number that we divided by. And if we get the dividend, then we are right. But if we do not get the dividend, it means that there's something wrong with our division. So that is one reason. The other reason is that when we are dividing, for each step, the result has to be included. For example, if we say 3 into 1 goes how many times, Jerry?
0.
Right. So we say 3 into 1, it will go 0, which means that the whole number of times that 3 can go into 1 is 0. If we put a 0 here, it would still be correct. So we could have placed the 0 there, but placing the 0 there would be insignificant because the 0 will not affect, that 0 will not affect the value of the number. On this occasion, we have to include that one because it is important to the value of the number. And this is the one that Jerry Lewis hates, and the grade 4 students are having difficulty with. As it is said, the grade 4 students, subtraction is one of their greatest downfalls. The subtraction sign tells us what to do. We will begin, as always, at the digits with the smallest place values, and those digits are located to the
Right.
Those are located to the right. Right, so those are located to the right. So 5 minus 0, and the result is
5.
if you have 5 things and you do not take any away, we will have what?
5.
All 5 of them still. So that goes right there. We cannot take 6 from 4, so we go to the greater place value and rename the 5. So let us rename that 5. We will reduce 5 by 1 because 1 will be taken to the column of less significance. The place value to the left is always 10 times the present place value. A single item from the left will have a value of 10 of the items in the present place value. So if we take a 1 from here and we are bringing it here, this is our present place value because we are actually taking the 1 from the place value that is to the left. The place value to the left is always 10 times the present place value. So the 1 that we take from here, which is 1 in the 1's position, will be what? 10 in the 10th position. So this one will be equal to 10 tenths. So we will say 14 minus 6, and the result is 8. Now, Jerry, what we have here is the one that was removed from here. The one that was removed is actually 10 tenths. So what we do here is we have 4 tenths and we have 10 tenths coming from the next column. So 1 tenth plus 4 tenths, that will give us 14 tenths. So this is actually 14. We intend to write 14, but because of the limited space, the 1 is written in a minute way. It is written in a small form in order that we may accommodate it, because we do not have additional space for this one to be placed so that it will actually appear to be our regular 14. But it is a 14 because we are taking 10 from here and we are adding the 10 to the 4, so that's 14. So vertically align the points with the ones that we have before, and then we say 4 minus 0 gives
4.
And then we say 9 minus 2, and that will give us
7.
What do we do with these 2?
Bring it down.
We'll bring it down because we do not have anything to be subtracted from it. There is no number to be taken from that 2, so it returns as it is. The correct answer is option
B.
Which fraction is the same as 5/6? Which fraction is the same as 5/6? We may use a method that is based on common sense rather than calculation. Two fractions can only be equivalent if the relative sizes of the digits are the same. This method is used to eliminate incorrect answers. So we will eliminate the incorrect answers by making use of the fact that the relative sizes of the digits must be the same if the fractions are the same. So let us take a look at that. Now what we have here is that the 5 is greater than the 4. Therefore, the 6 must be greater than the 16 if the fractions are equivalent. If not, then those fractions cannot be equivalent. So if the fractions are equivalent, 5 is greater than 4. So the 6 must be greater than the 16. If not, then this is for sure an incorrect answer. The numerator on the left is smaller than the one on the right, which is this one is smaller than this one. The fractions are only worth comparing if the denominator on the left is smaller than the one that is on the right. If not, we will have to eliminate that fraction as a possible correct answer. So, because the 4 is smaller than the 5, then the 16 must be smaller than the 6. Because it is not, then we are sure that this option cannot be correct. The denominator on the left is larger. Since the fractions are inconsistent, then they cannot be equivalent. Make a go at that one. 5/10 and 5/6. Those cannot be equivalent. Why? Because the numerators are equal and the denominators are different. So the fractions cannot be equivalent. In this case, the numerators are the same. The fractions can only be the same if the denominators are the same, in which case the fractions will be identical. Those are different. The denominators are different. This causes the fractions to be skewed. They cannot be equivalent. By those quick comparisons, we have eliminated options B and C. On the next slide, we will take a look at why the quick comparison is mathematically legitimate. Let us take a look at 3 ways in which we may show that fractions are equivalent. If by reducing one by a common factor we get the other, the two fractions are equivalent. So let's go at it. We have 10/15 and 2/3. we are reducing here by a common factor of 5. So 10 divided by 5 is equal to 2, and the factor of 5 into 15 is equal to 3. So we have 15 divided by 5, and the result is 3. We are reducing by a common factor of 5. The fraction reduces to 2 over 3, which is 2/3, the same as the other. Multiplying numerator and denominator by the same number results in the other. So that is the first one that we did. The first one is that we reduce the fraction by a common factor, and the other one is the result. Then we are sure that the two fractions, 10/15 and 2/3, are equivalent or equal. So the other way to tell if fractions are equivalent is by multiplying the numerator and the denominator of the fraction by a common factor. So we are multiplying both numerator and denominator by 2. Right, a common factor of 2. So 3 2s,
6.
2 7s.
14.
Right. So the result is 6/14, which is the same as the other. Therefore, the two fractions are equivalent. If we reduce the two fractions and the results are equal. So if we have two fractions, we reduce this one by a common factor of what? Jerry is saying a common factor of?
3.
Then what will we reduce this by? A common factor of?
4.
Right. So reduce this one by a common factor. Why can we reduce this one, Jerry, by a common factor of 3? Because 3 can go into both numerator and denominator. So 9 divided by 3 is?
3 times.
And 12 divided by 3 is?
4.
4 times. So that fraction turns out to be 3, right, or 3/4. And according to Jerry, we need to reduce this one by a common factor of what?
4.
4 into 12
3 times.
and 4 into 16.
4 times.
Okay. They both reduce to 3/4. They are equivalent fractions. Now, if the fractions are equivalent, we may prove that by dividing both. It means that both numbers will get smaller. And if we can do that by multiplying both numerator and denominator, it means that both numerator and denominator will get larger. Option A is incorrect. There is no natural number that you can reduce 6 by, and the result is 5. Reduce option D by a common factor of 2. So we will reduce option D by a common factor of 2. So option D, reduce that by a common factor of 2, we get?
5.
Right, 2 into 10 is 5, and then 2 into 12 will be?
6.
Right, so we say 2 into 12 is equal to 6. Do we get the result that we have here for the fraction that we are trying to see if one of these options is equivalent to?
Yes.
Okay, so we have 5/6 when we reduce 10/12 by a common factor of 2. This results in the original fraction. So we reduce option D by a common factor of 2, and the result is the original fraction that we have in the statement of the problem. Because this is so, then we are sure that the correct answer is option D. Multiply numerator and denominator of the original fraction by 2. So we have the original fraction, which is 5/6 that we have right here. We will multiply by 2, and what do we get? 5 2s?
10.
6 2s?
12.
Right. So we may take any of the two approaches in arriving at our correct answer, which is we take the one in the option and we multiply both numerator and denominator by a common factor of 2, or we may take the one in option D, then reduce the fraction by a common factor of 2. So we may increase one or we may reduce the other. The results that we get is a fraction that is in option D. By reducing the fraction, both numerator and denominator will be smaller. So that is the question that we were trying to figure out earlier on. Why is it that when, for example, we compare the fraction with b, in this case, the numerator is smaller than this one, but the denominator is larger in this particular case, that this cannot be a correct answer? It cannot be a correct answer because in order to get equivalent fractions, we will have to either reduce by a common factor, in which case both numbers will be smaller than the original, or we need to multiply by a common factor, that is multiply both numerator and denominator by a common factor, in which case both numerator and denominator will be larger. It is that either both will be smaller or both will be larger. So if we have the numerator larger and the denominator smaller, then we know that that cannot possibly be an answer, or that cannot be a possible answer for equivalent fractions. We will prove that multiplying both denominator and numerator of a fraction by a common factor will give a fraction that is equivalent to the first. That is what we are attempting to do. So we are attempting on this occasion to prove that if we multiply both denominator and numerator of a fraction by a common factor, that the new fraction that we will get is actually equivalent to the first. And we imagine that it can be mathematically achieved, but we are about to show that it can be physically achieved. Now, before we move a step further, Jerry, this figure that we have here, how many equal parts is it divided into?
4.
We have 4 colors right there representing the 4 equal parts in which the figure is divided. The shape that we have is divided into 4 equal parts. Our original fraction is 3/4. 3 parts out of 4. That is our original fraction. 3/4. 3 parts out of 4. So we have right there 3 parts shaded out of a total of 4 equal parts. Bearing in mind that the shaded portion represents 3 out of 4, Let us further divide the whole into how many equal parts we will go for now, Jerry?
8.
8 equal parts. So what we had there before represents how many equal parts?
4.
Right. And the one that we are going to be dividing into, like we are going to be dividing into at this present time, will be how many equal parts?
8.
8 equal parts. So there we have 8 equal parts. How many parts out of 8 are shaded? You want to take a go at it now, Jerry? We have the same number of parts out of 4 shaded. Don't answer that question just yet, Jerry. How many parts do we have shaded out of the 4?
3.
We have 3. Do we still have 3 parts shaded out of 4?
Yes.
Okay. Now that it is divided into 8 equal parts, how many equal parts is it divided into, as you can see?
6.
Right, so we have that divided into 8 equal parts, and the number of equal parts that are shaded are
6.
6 equal parts. How many parts out of 8 are shaded? 6. So here we have 3 quarters being multiplied by a common factor of 2. So both numerator and denominator will be multiplied by 2. So we have 3 times 2 equals
6.
and 4 times 2 equals
8.
Alright. So here's your question, Jerry. We multiplied by 2 both numerator and denominator. And the result is
6 and 8.
8. Right. What does 8 represent in the figure that we have over here, Jerry? What does 8 represent?
The denominator.
Right. So 8 represents the denominator. And the 6 represents the
Numerator.
Right, so Jerry is saying that the 8 represents the denominator. Of course, 8 is the denominator. It means that the second division of the whole is into 8 equal parts. And the first division was 4 equal parts. But when we count the number of equal parts shaded in the new division, we have 6 parts out of 8. We have 6 parts shaded out of 8 equal parts. This represents 6/8, which is the same fraction that we get when we multiply both denominator and numerator of 3 quarters by 2. So what we are saying is that if we multiply both numerator and denominator of 3 quarters by 2, we get 6/8. That's right?
Yes.
And we are saying that if we have 3 quarters and we make other subdivisions, dividing each quarter into 2 equal parts, then we will have a total of 8 equal parts, and the number of equal parts that will be shaded is 6/8. So we are showing here that if we do the calculation, the equivalent fraction is 6/8. And if we use physical subdivisions, the result will be what? 6 parts shaded out of a total of 8 equal parts. So we are sure that actually multiplying both numerator and denominator of a fraction by a common factor, we are sure that we will have an equivalent fraction. There we have it. The fraction 3 quarters, 3 parts out of 4, is actually the fraction 6/8, 6 parts out of 8. As shading 3 parts out of 4 is the same as shading 6 parts out of 8. Right. How does this relate to the mathematical process of multiplying both numerator and denominator of the fraction by a common factor? Multiplying the numerator and denominator of 3/4 by a common factor of 2 results in 6/8 that we have already proven to be equal fractions. Therefore, multiplying both denominator and numerator of a fraction by a common factor does not change its value. So the fraction has the same value, but the form of the fraction is different. Just the numbers are different, but they are equivalent fractions. That means 3 parts out of 4 will be the same as 6 parts out of 8, as we show right here, and we show that it can also be achieved by multiplying the numerator and denominator by a common factor of 2. On this occasion, Jerry, we do not have any statement of the problem with the exception of this form that we have right here. And this form is telling us that we should do what with those numbers?
Add.
Right. And the result that we get should be in?
Dollars.
Right. And recently, I'm seeing on the internet figures telling you how much money you can make in a day. And those figures have the dollar sign not to the left as we have right here, but to the right. So I am skeptical about those programs that I see on the internet. And we will begin on this occasion also, like every other occasion, to add the digits that are to the extreme
right.
So we'll begin by adding the digits to the right. Those will be our least significant digit, or digits that are of the least place value. And those digits that we have to the extreme right, what is their place value, Jerry?
Hundredths.
Right. Hundredths is correct. So in this problem, the numbers are already presented in the way that we may add them. Begin by adding the digits to the extreme right. They have the smallest place value. And when we add those, what do we get, Jerry?
11.
I'm trying to ask the question very quickly to see if Jerry's answer will be forthcoming, and it is, because Jerry likes to be in situations in which he has to add or multiply digits very quickly. That's the game that Jerry likes to play. It's 11, so 3 plus 5 plus 3, and that is equal to 11. Write down 1 and carry 1 to the next column. Why do we do that? Because this is a ones digit. This is a tens digit. The digit of greater significance is brought over to the column of greater significance, and the column to the greater significance is located to the
left.
Right. So move on to the next column. I'm going to try to catch Jerry with this one. When you add those, what do you get?
15.
Right, he's right on the ball again. So when we add those, 1 plus 6 plus 6 plus 2, the result is 15. Right, so we have 6 2's 12, and on the extreme we have 3. So 12 plus 3, that's 15, if you want to take a look at it that way. So write down 5 and carry 1 to the next column. So the tens digit of greater significance will be brought to the column of greater significance. Remember that the column to the left is always 10 times the present place value. So if we are at tenths, the ones will be 10 tenths. So 1 is 10 tenths. So the tenth digit of the sum that we have here will always be carried to the column to the immediate left, in which the place value is 10 times the present place value. Vertically align the point with the other, so we have to put our point down also in its rightful place. And let's go again. When we add those, Jerry, what do we get?
15.
Maybe Jerry is doing it while I'm doing something else. So as soon as I ask, he has the answer, which is very smart. Or maybe he's doing it right on the spot. But that's not very difficult, because 5 plus 5, that's
10.
And then we just add these into it, and that's 15. So add the digits in the next column. When we add those, we have the two 5s together will give 10, and we know 1 plus 4 is 5 again. So that's 15. Write down 5 and carry 1. And that is equal to?
12.
Okay, Jerry is on it again. 12. So add the digits in the next column. So we have 1 plus 2 plus 9, and that is equal to 12. And we will put the ones digit of 12 down and carry the tens digit to the left, which we find the digit of greater significance, which is 10 times the present place value. And finally, when we add those, what do we get?
3.
Right. So finally, add 1 plus 2. The answer is 3. And that is the result of the last column. And Jerry, what do we say? That is represented by option?
That's represented by option A. Something is left off, the dollar sign.
Right, so we have to include the dollar sign. I was waiting for that before. Jerry said that is what? Option A. I was listening for the dollar sign. But Jerry gave the option first and then also mentioned that we need to include the dollar sign. And we do not include it to the right, as on the internet. We include it where?
The left.
Right. The correct answer is option A. Which is a multiple of 18? Which one of these is a multiple of 18?
36.
Right. 36. Jerry is saying that it is 36. I hope that he is right. Let's see if Jerry is correct. A multiple is the result of multiplying by a natural number. Multiples of 18 are the results that you get when you multiply 18 by members of the set of natural numbers or counting numbers. So what is a multiple? The result of multiplying by a natural number. So multiples of 18 are what we will get if we take 18 and multiply 18 by any member of the set of natural or counting numbers. Write down some natural numbers. So there we have some natural numbers. And we have the symbol that is representing natural numbers there. The symbol that we have above those numbers is representing natural numbers. And that is a fancy N, or it is an N with a diagonal stroke or double diagonal stroke, as we have it right there. So that is your symbol for a natural number, or the set of natural numbers. If we multiply each by 18, the result will be multiples of 18. So if we multiply each by 18, the result will be a multiple of 18. So multiply 1 by 18 is 18. 2 multiplied by 18 is?
36.
And that is our correct answer, which is represented by which option?
D.
Right. And we have some other multiples of 18. 4 times 18 is 72. So 72 is a multiple of 18. Let me ask Jerry. What about 180?
Yes.
Is it a multiple of?
18.
Jerry is saying that yes, it is a multiple of 18. What natural number do we multiply by 18 and the result is 180, Jerry? What natural number do we multiply by 18 to get 180?
10.
Right. So when we multiply 18 by 10, we get 180. Therefore, 180 is a multiple of 18. Only option D is among the multiples of 18. It is therefore correct. So of all of the numbers that we have there, only 36 is present in the multiples of 18. So 36 is our correct answer. Factors and multiples are closely related. So although we have already located our correct answer, we need to take a look at some other aspect of our mathematics. We just don't want to just say what is a multiple and just say 36 is a multiple and then we just move merrily along. And there are other things that we need to learn. So factors and multiples are closely related. When we multiply two natural numbers, the result is called a multiple. The two natural numbers that we multiply are called factors. So when we multiply the two factors together, the result is a multiple. The result is a multiple. Alternatively, a multiple is a number that others may divide into without a remainder. So a multiple is a number that others may divide into without a remainder. So there we have 20, 50, and 35. So I'm asking you, Jerry, what number may divide into those numbers without leaving a remainder?
5.
Right. So those numbers are therefore multiples of 5 because 5 can divide into them without leaving a remainder. Those numbers are multiples of 5 because 5 may divide into them without leaving a remainder. And we say because they are divisible by 5. So when something divides without a remainder, the word that we use is divisible. So those numbers will be divided by 5 without a remainder. Therefore, those numbers are divisible by 5. A factor may be defined as a number that may divide into another without a remainder. So we have 2, 4, 6, 8, 9, and 12 are factors of 72. Why are they factors of 72? Because they all may divide into 72 without leaving a remainder. Also, we may say that 72 is divisible by each of those numbers. So those numbers are factors of 72. They may divide into 72 without a remainder. What is 1 and 1/5 plus 2/5?
1 and 3 over 5.
And Jerry is saying 1 and 3 over 5, but Jerry is speaking to himself these last days. So 1 and 3/5. Let's see how we may arrive at that. When adding mixed numbers, the whole numbers are added and the fractions are then added. There is one whole number. So when we are adding mixed numbers, the whole numbers are added and then the fractions are added. And some might add the fractions first, because when adding the fractions, it is possible to get a whole out of the sum of the fractions. And that whole, or those wholes, may be added to the whole numbers. So it is easy to add fractions if their denominators are the same. So we have the whole number there, and we may go straight ahead and add those fractions. So we are labeling the fractions, showing your numerator and your denominator. And do not forget that the dividing line between the numerator and denominator, and I'm going to ask Jerry, what is that dividing line called?
The fraction bar.
Right, it is called the fraction bar. When the denominators are the same, the resulting fraction will have the same denominator as the fractions added. So, the result will have the same denominator as those two. So we are writing down the result of 1 1/5 plus 2/5. The resulting fraction will have the same denominator as the two fractions, because we are adding fractions with the same denominator. The resulting numerator will be the sum of the numerators. So take those two numerators. What are the numerators, Jerry?
1 plus 2.
Right, so we will have 1 plus 2 for the answer in our numerator. Is there anything missing, Jerry?
The whole number.
Right, the whole number. Jerry is very sharp to say that the whole number is missing. Very nice. So don't forget the whole number. So we'll have 1 plus 2, and that will be equal to?
3.
3. And then we will have the whole number. So we will have 1 3/5. And that will be our correct answer. And that is represented by which option?
Option A.
And that is represented by option A. Now we have a serious problem right there. What is 4 minus 1/8? What is 4 minus 1/8? And 4 is given as a whole number. All right. Do you have your answer as yet, Jerry? Right, not yet. We are about to subtract a fraction from a whole number. But it is more convenient to subtract it from a fraction, especially one with the same denominator. Did you hear that, Jerry?
Yes.
We need to subtract 1/8 from 4, which is a whole number. And we are saying it is better to subtract 1/8 from what? From a fraction. And it is better if the fraction, or best if the fraction that we are subtracting 1/8 from will have the same what? Denominator. How do we do this?
Answer is A.
Right. So let us go straight ahead and do the subtraction. So there we have 4 minus 1/8. 4 minus 1/8. There are many ways that we may do this, but at this level, the one that we are going to be taking a look at is the most convenient way. Our first step is to take the 4, which represents 4 wholes, and separate one of the wholes. So we will separate the 4. We are going to make the into what? We are going to make the 4 into 4 wholes. We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to make the 4 into what? We are going to into what, Jerry?
4 wholes.
The 4 wholes that we have there will be represented by what?
3 plus 1.
Right, 3 plus 1. So we will take out one of the wholes from the 4, and we will have 3 left. So we will say that 4 is 3 plus 1. There we have it. Now, the 1 that we have here is the one that we will take away the 1/8 from. Right, let's see if Jerry can figure out what this 1 is equal to if we are going to write it as a fraction with the same denominator. The 1 is equal to what, Jerry?
8 over 8.
It is going to be represented by 8/8. So the 1 will be represented by 8/8. The whole must be divided into the same number of equal parts as indicated by the denominator of the fraction. The denominator indicates 8 equal parts. So if we have 8 equal parts here, then we need to divide this whole into 8 equal parts. So it is represented by 8/8. So if we have a whole may be written as 5/5. It may be written as 4/4. It may be written as 3/3. But because we are subtracting 1/8, then we will write it as 8/8. When an object is divided into a certain number of equal parts, the whole is the total number of equal parts. If it is divided into 5, the whole is 5 parts out of 5. In this case, it is divided into 8. The whole is therefore 8 parts out of 8. Do not forget what we have, Jerry, that we first took the 4 and we write that as 3 plus 1. And then this 1 whole will be written as a fraction with the same denominator that we have here. And the whole is therefore represented by 8/8. So it is written as 8/8. So on the next slide, we will complete the process. This problem is analogous to number 9, except in that we are subtracting on this occasion. So it's a similar problem to number 9, with the exception that on this occasion we are subtracting. Do not forget that we have 3 wholes. The problem is already simplified by converting the whole number to a mixed number with the fractional part having the same denominator as the fraction that we are subtracting. Do not forget that the 4 was written as 3 plus 1. Not only that, but we will write the 1 as a fraction with the same denominator as the fraction that we have there. So it will be represented by 8/8. The denominators are the same. If the denominators are the same, Jerry, what do we expect the denominator of the answer to be?
8, and just the same.
Right, it's going to be 8, which is the same as the ones that we have there. The resulting fraction will have the same denominator as the fractions that we are adding. And what do we do with the numerators?
Subtract.
And when we subtract, the result will be?
7.
Okay. So the resulting numerator will be the difference between the numerators, like we have right there. What is missing, Jerry?
The whole number.
The whole number is missing that we will include. And while we are including the whole number, we will complete our subtraction process. And that will give us the correct answer of Which?
Option B.
Option B. So the correct answer is option B. Which has the greatest value? Which one of those numbers, Jerry, can you see has the greatest value?
61,675.
Right, so Jerry is saying is 61,675. And how did Jerry arrive at that answer? Jerry is correct. The correct answer is option A. In this particular case, we are just putting in the place values there just as a constant reminder, because the digits or the numbers all have the same number of digits and the same place values. Therefore, making a comparison may be easily done without including those place values. Look at the place values of the digits. They are not so important because only the order of the sizes are important. And the leftmost one is the largest. So we may remove those place values because the most important thing in the place value is the relative sizes of those place values. And we know already that if we are at a particular location, the place value to the left is 10 times the present place value. Also, if we are at a particular location, the place value to the right is 1/10 of the present place value. Or we may say the present place value is 10 times the place value that is located to the right. The leftmost digit contributes the most to the value of the number, and it is called the digit of, what do we always say that it is? The digit of greater, right?
Greater significance.
Right, so the digit of greatest significance that is located to the left, or the one that we call the leftmost digit. The leftmost digit is the one that contributes the most to the value of the number. It is called the digit of greatest significance. That one. So we are taking a look at that. The one with the largest digit there will be the largest number. So if we are just looking right at those leftmost digit, Jerry, which one would you say is the largest number?
6 and 6.
Right. So the ones that contain the 6, as a matter of fact, we are looking for the single largest number. But on this occasion, we have the leftmost digit of 2 of them. Well, the 2 largest being the same. So the largest digit that we have there is a 6, and it is present in 2 of those numbers. So we cannot just look at those leftmost digit and come to a conclusion as to which number is the largest. But what we can do is, because we have 2 other leftmost digits that are smaller than these, we are sure that these cannot be the largest number. They all have the same number of digits, and hence their leftmost digit will have the same place value. However, there is a tie for the largest digit in the largest place value column. So because there's a tie for the largest digit in the largest place value column, we cannot come to a conclusion as to the largest number. Based on that, although Jerry told me that the largest number is 61,675, which is correct. We cannot come to the conclusion based on the leftmost digit, although if we could single out the largest leftmost digit, then that would represent our correct answer. But we have a tie. On the next slide, we will go through the finer details of the solution of the problem because of the tie. So there's a tie, so let us take a look at what we will do. There is a tie between option A and option B for the largest digit in the most significant position. So, cancel the other numbers. Neither of them can be the largest. So we'll just take those out. They cannot be the largest, because their most significant digit is smaller than the one that we have there. Now what do we say, Jerry? We are comparing the next in line, and what do we notice?
There's a tie with
There's,
the ones.
there's a tie with the ones. And because there is a tie here in this place value column, what do we do? Do we stop and say that we cannot find the answer?
No.
What do we do?
We go to the hundreds line.
Alright, so we go to the hundreds digits and we compare. So they are still equal, so we will still have to go to the digit of less significance. The digit in A is 6 and the one in B is 5. The correct answer is option
A.
Why is it the correct answer?
Because 6 is greater than the 5.
Right, because the 6 is greater than the 5. So we are sure that that is our correct answer, option A. The leftmost digit is called the digit of greatest significance because it contributes the most to the value of the number if it is not equal to 0. So if the digit of greatest significance is not equal to 0, then it will contribute the most to the value of the number. It does not matter what the digits of less significance are. The number with the largest digit in the most significant place value position will be the largest number. Look at the numbers and the place values of the digits. Take a look at that, Jerry. Which number is larger?
10,164.
So Jerry is saying that it is 10,164. At the same time, we have only a 1 here. But we have a 9 here, which is a larger digit than the 1. How comes do we say that the 1 with the smaller digit in its most significant position is larger than the number with the very large digit in its most significant position? Why do we say that? The one at the top is 9,785. The other one is 10,164. Although the most significant digit in the first number, which is 9, is far greater than the most significant digit of the second, which is 1, the second one is greater than the first because its most significant digit is of a higher place value. Although the most significant digit in the first number is 9, which is far greater than the most significant digit of the second, which is 1, the second one is greater than the first because its most significant digit is of a higher place value. In determining the relative sizes of numbers, place value takes precedence over face value. It does not matter how many thousands the other number has. The one with tens of thousands will be the largest. So it does not matter how many thousands we have here, as long as we do not have a zero here, then tens of thousands will be larger. What are we attempting to do on this slide, Jerry? There we have 2,185 and we have 1,816. In this particular case, the place values do not matter too much because the numbers have the same number of digits, and hence the place value of the most significant digit will be the same. The one at the top is 2,185. The other one is 1,816. Although the second number has by far the larger number in the second most significant position, it does not matter. This is because the top number is over 2,000, while the other one is under 2,000. So of course, if this digit were a 9 and this one were a 0, as long as this is a 2 and this is a 1, then this number will still be larger than this one, because the top number is over 2,000 while the other one is under 2,000, and that is because of the place value that we have there, that the larger number is in the largest place value position. The place value of a digit is the value that it has because of its relative position in a number. Its face value is its actual numerical value. For example, the actual numerical value of this digit is 8. That is its face value. It is in the hundreds column. Its place value is hundreds. So it is actually 8 hundreds. In the following number sentence, what is 15 called? Factor, product, remainder, sum. It is called what?
Factor.
Right, it is a factor as we discussed before. So we will not have to go through a lot of rigmarole just to say why it is a factor. We may just say that it is a factor and we are done. Factors and multiples are closely related, as we said before. When we multiply two natural numbers, the result is called a multiple of the two numbers. The two natural numbers that we multiply are called factors of the result. So these two are factors of 120. 120 is a multiple of both 8 and 15. Option A is therefore correct. It is a factor. When we multiply two numbers, the result is called the product. Therefore, in the number sentence, 120 is also called the product of 8 and 15. When numbers do not evenly divide, a remainder is left. So we are talking about factor, which is the correct answer. We talk about the product. We are discussing product, and we will now discuss remainder. When numbers do not evenly divide, a remainder is left. A sum is the result of adding two numbers. So what is a sum? The sum is the result of adding two numbers. When we add numbers, each one of them is called an addend. The result of addition is called the sum. Let us divide 15 by 6. When we divide 15 divided by 6 is what? What do we say 15 divided by 6 is what, Jerry? How many times can 6 go into 15?
2 times.
Right, 2 times. Because if we know our multiplication table, we know 6 1,
6.
6 2s,
12.
6 3s.
18.
Right. So 6 3s 18, 6 2s 12. 12 is smaller than 15. That means since 6 can go into 12 2 times, 6 will be able to go into 15 2 times. But can 6 go into 15 3 times?
No.
Why? Because 6 3s?
6 3s 18.
Right. So, and 15 is smaller than 18. So 6 will not be able to go into 15 all of 3 times. So 6 into 15 will give us a result of 2. 6 into 15 will give us a result of 2. We say 6 into 1, we can't. Then say 6 into 15 goes
2 times.
2 times. Although 6 will go into 15 2 times, 6 times 2 is not equal to 15. 6 times 2 is equal to
12.
Right. And if we subtract that 12 from 15, what will happen?
You have a remainder of 3.
Right. We will have 3 left over. So the result is 3 that is left over, and that is our remainder. So when we are dividing, 6 into 15 goes 2 times. Right. 2 is our quotient, and we have a remainder of 3. So 3 is our remainder. Even if we are dividing 15 by 6 by physically manipulating objects, the remainder will be the number of them that are left over. The remainder will be the number of them that are left over. So even if we are dividing 15 by 6 and we are doing that by manipulation of objects, so we have 15 objects and we are dividing those objects by 6. Even if we are doing that physically, as we will do in a few seconds, the remainder will be those that are left over. So we have 6 there. So we take out 6 of them. And then we have another 6. We'll take out another 6. There we take out another 6. And what do we notice?
3 is left.
Right, 3 hearts are left. How many groups of 6 do we have?
2.
We have 2. There are 2 groups of 6, and there are also 3 leftovers. There is therefore a remainder of 3. Here the remainder is more clearly seen because we have an extra 3 objects that do not make a complete group of 6. So the remainders are those that do not make a complete group of 6. And how many do we have there that do not? How many? Not how many groups of 6, Jerry. How many do we have there that do not make a complete group of 6?
3.
Right, there are 3. So those are our remainders.